Good guys, so welcome to the Material Joining Laboratory. Let me also start the recording. Okay. Can you see my screen? Yeah, Tosif? Okay, good. So we'll start the class on Material Joining Laboratory. Okay, so we will try to make as lively as possible this class. I removed the mask just to show my face for the video. Okay, so the course roll number is MM5770, right? So we are going to look at the number of demonstrations in the Material Joining Laboratory course. The lab is actually conducted in our lab, which is called as Joining and Additive Manufacturing Lab. Okay, it's pity that we cannot conduct this lab in person. So we would be really glad to have you here. But maybe once you are back to campus, you're feel welcome to come to our lab, and then subsequently you can also explore. But time being, we'll have this class in online mode, like what we are doing now. Okay, so what is the objective of this entire lab course? Okay, if you look at what we are actually planning to give is to impart practical knowledge of welding and joining processes. Okay, so we have a number of processes. Some of you must have already attended a welding processes course. Okay, so starting from fusion welding, okay, solid state welding, fusion welding, arc-based processes, power beam processes. Okay, in solid state welding we have friction-based processes, right, and so on and so forth. In our lab, joining and IT manufacturing lab, we have a number of welding processes. So we are going to do demonstration of all the processes that we have in our lab. And added to that, so we also have some physical simulation facilities. For example, what is known as Gleeble. Okay, so Gleeble can be used to simulate, okay, thermal cycle that is actually prevalent in a welding process. Okay, so we will also conduct one demonstration on simulation, how the physical simulation facility such as Gleeble is very useful in understanding the various physical phenomena that are happening during welding. Okay, so we would use that facility along with all the welding equipment to understand, okay, the practical usage of this equipment, various process parameters that are influencing the welding process, as well as how effectively we can control these processes to achieve required weld mechanical properties. Okay, so that's the primary objective of this course, to impart a practical knowledge of welding and joining processes. So along with the welding processes, we also have a new additive manufacturing facility. Okay, so based on laser powder bed. If time permits, one class we will also have a demonstration of that facility as well at the end. Okay, so what is the tentative schedule? If you can now see, sorry. Okay, so we are going to have about 9 sessions. Okay, if time permits, we can also go to, as I said, a laser powder bed facility as well. Okay, at the last class. Today we are going to have an introduction about the lab. Okay, once I finish the slides, we would roam around the lab to have a look at the facilities close by, and we will also explain some basic about the equipment which we are going to use for this lab class. So once we finish that, okay, so we will start looking at first exercise, so which is the demonstration of shielded metal arc welding. Okay, so shielded metal arc welding. So some of you must have already aware of that process from welding processes course. Even if you are not aware, doesn't matter. Okay, so we will give some basic introduction. So in this process, okay, what we are going to use as an electrode, and then the power source, and a basic welding experiments we are going to show today. Okay, so cylinder metal arc welding is also known as manual metal arc welding or stick welding. Okay, it is one of the most commonly used processes for day-to-day welding, construction industries, simple white goods fabrication, and so on and so forth. So that is today's session. So then we'll move on to, okay, so next week, demonstration of gas junction arc welding. Okay, so in a gas junction arc welding, okay, we use a non-consumable electrode, right? So tungsten electrode is used to strike an arc, and we use a shielding gas, primarily argon, okay, for striking an arc. And in this experiment, we are going to look at welding of stainless steel plates. So how the stainless steel plates are welded using this facility, and we would also demonstrate, okay, the temperature measurements in the heat affected zone. Okay, so how a data accuracy system and a thermocouple attachments can be used to measure typical thermal cycles that are actually evolving when we do this welding. Okay, so that would be next week. And once we have that experiment done, these thermal measurements subsequently would also be used for fourth week. Okay, so when we do Gleeble simulation, so we will extract the thermal profile during welding in second week, and that would be input for simulations in Gleeble in fourth week. Okay, so that is fourth week experiments. In between third week, okay, we will also have our demonstration in a plasma welding. Okay, we have two specialized torches. So one is a high power plasma, okay, and the other one is a microplasma. So in a conventional plasma setup, we use a big orifice. Okay, so again we will demonstrate that later. So in plasma welding, in a conventional plasma, we have a large water cooled copper nozzle with orifice diameter more than 1.2 mm. Okay, and that setup, and then subsequently we will also look at mycoplasma welding. Okay, so in mycoplasma we use arc constriction, okay, which much smaller diameter. So both processes will have a demonstration in third week, right? So as I said, in the fourth week, possibly on 16th of February, so we would use a Gleeble for simulating the thermal cycles we measure during second week. Okay, in a gas junction arc welding, so we get the thermal profile extraction, right? So using those information, we would carry out physical simulation in Gleeble, okay, and then understand, okay, so how such a physical simulation is really valuable in controlling, okay, to physically simulate and understand the microstructure evolution, okay, in the heat affected zone. Okay, so we'll have a demonstration of that. Okay, so once we have done that, we can move on to the other consumable welding process, okay, which we use extensively for various applications, that is gas metal arc welding. Okay, so in gas metal arc welding, so we would also do a demonstration of conventional constant current, okay, gas metal arc welding, which actually uses free flight transfer. Metal transfer would be in free flight mode. Okay, so we would have a conventional gas metal arc welding process, and then subsequently, okay, we would also see other types of metal transfer modes. Okay, for example, controlled dips or circuiting. Okay, so commercially this controlled dips or circuiting is actually known as CMT process, okay, cold metal transfer. It's a variant of gas metal arc welding. Okay, so we would have a demonstration of these two processes, including we will also see how the metal transfer is changing as a function of multiple current inputs we give. using an high-speed video. Okay, so high-speed video imaging. Okay, we are going to demonstrate using an high-speed camera to look at how, say for example, we have a consumable electrode. So this is contacted when the droplet is detached, okay, and transferred to the molten pool. Right, the modes of this metal transfer we can visualize using an high-speed camera. Okay, so that would give you a good demonstration about how consumable welding process work. Okay, in say constant current mode or in controlled dip short circuiting mode. So short circuiting mode where the droplet is detached by the short circuiting. Okay, so the wire would be dipped onto the molten pool and the surface tension, and the addition of slight increase in current can also give additional detachment force as a form of Lorentz force. Okay, so we will see that in this demonstration. When the class starts, we will also see some physics of it. Okay, a couple of examples in live. So once we finish that, and the next week we'll move to the one solid state welding process. So we'll have a demonstration of friction stir welding. Okay, so friction stir welding, we all know that it is a solid state process in which we use a tool, and which is actually made to plunge onto the interface to be joined, and then we have a mechanical deformation enabling coalescence between the fairing interfaces. So we would have one exercise where we use aluminum base plates are welded using a tool steel tool. Okay, so we'll have the various parameters, the role of the effect of these parameters on the welding, and we'll also see the effect of the rotation speed, okay, and the axial loads what we apply on the weld geometry. Okay, so once we finish that, so we'll move on to the resistance spot welding. Okay, so resistance spot welding, that again from my welding process course. So it is one of the most used welding processes in automotive industry. Right, so in automotive industry, so we primarily use resistance spot welding to weld thin sheets. Right, so for example, if you look at on auto bodies, we have a number of spot welds made. So we have two equipment. So one is a conventional spot weld, which uses a copper electrode, so which can be used to weld the steels, automotive steels, with a thickness of 2 to 3 to 3.5 mm. And we also have one most advanced equipment for resistance spot welding, so which is known as delta spot. Okay, which uses consumable strips as electrodes. Okay, so there is a subtle difference between using a standard copper electrode or a strip electrode. Okay, so we'll also have one demonstration from a delta spot. Okay, so, and then we can compare how the conventional spot welding vis-a-vis the delta spot welding can change the weld geometry, weld nugget size, as a function of the primary welding parameters for resistance spot welding are, okay, so welding current, okay, the load we apply, and welding time. Okay, so we'll see how the variation can influence the weld growth. Okay, so once we finish that, so we'll move on to the next welding process demonstration. So that is actually magnetically impelled arc butt welding. Okay, so that is nothing but, okay, we call shortly, in short name, MIAB. Okay, MIAB welding. So MIAB welding is a variant of a flash butt weld. Okay, in this process, so we use permanent magnets to impel the arc. Okay, so by doing so, we can enhance the heating efficiency at the fairing interfaces. So once we ensure uniform heating, so we can do an upsetting, which can give us an excellent weld, okay, in circular geometries for welding pipes, okay, or rods, okay, so, or tubes, and this is one of the best processes. So we'll have a demonstration of this. So just to make a point here, okay, so these equipments, Delta Spot and MIAB, okay, are very unique equipment, and you don't find them not many places in India. Okay, and MIAB welding, there are only 2 equipment in India. Okay, so one is in our lab, and other one is in WRI, which is very small. So fully industrial scale, okay, MIAB welding. So we are going to see from our lab, and which you cannot see in much places. And the Delta Spot you can't find anywhere in India except in our lab. Okay, so it can be interesting for you to look at both the facilities and how they work in real life. So by the time we finish MIAB, okay, so we would be mid of March. So we are planning to complete on 16th of March, and 1 week if time permits, on 23rd we will also give a demonstration in our 3D printing facility. Okay, so we have installed a laser powder bed fusion facility, right? So this facility right now, okay, it's installed in our lab on 23rd March. So we'll see if we can give a demonstration. Yeah, we will see. So with that, we'll wind up these labs, and then we'll conduct. Okay, so from 30th of March and April, by Govas. So there could be some change in schedule, and we may even add 1 or 2 labs demonstration if time permits, depending on the equipment status, because these equipment are prone for maintenance, right, requirement. So if sometimes equipment may be not functioning as we expect, or maybe we may see some uncertainties in conducting lab, so we may have to switch back and forth, or we may have to add, if time permits, 1 or 2 sessions in any of these, or in some of the equipment. Okay, so this is the tentative schedule of the lab, and if you have any questions, you can ask me now. Okay, so let me turn my camera on. Okay, any questions, guys, so far? Okay, so I will also demonstrate. See, guys, you are expected to submit, okay, every week through Google Classroom. Whatever you learn from this class, you will have to submit the report before next week class, preferably by the weekend. So we have every Wednesday class, right? By Sunday evening, you should submit the report, okay, in Google Classroom. The videos will be shared, preferably, possibly by end of the lab class. So if you are doing lab class on Wednesday, by Wednesday night, so you may see the videos appearing in the Google Classroom. So you can watch the videos, right, and then you'll have to submit the report by summarizing what you have seen in the lab class. Right, so you will be evaluated for the report and the final viva voce. So report and attendance, okay, attendance in the sense, how early you submit the report, okay, or how good is the report, would carry 50 marks, and then final viva voce would carry 50 marks. Okay. Any other questions, guys? Hello? Yes? Yeah, Praveen, go ahead. There is no real format. Okay, so you can just give an introduction, okay, and introduction about the process, what you are seeing in that lab class, okay, and your observations, so the theory behind the technique, what you are seeing, and the actual experiments which is demonstrated. Suppose in gas tank arc welding, you must be seeing a demonstration of first about the equipment, the power source, okay, the torch design, the material to be welded, okay, the welding process parameters used, right? So all these things you need to report, and then it should also give some theoretical understanding. Imagine, suppose if a technician is demonstrating, would also say that the role of welding current. So he may be setting, say, 100 amperes as a current. Okay, so you can ask him why 100 amperes. Okay, and if you change the current to 100 from 120, okay, so what would happen? And if you change the welding speed, how would that influence the arc energy? Okay, so how does it influence the heat input? So it's nothing but efficiency times arc energy, right? So some fundamental understanding you should gain from this demonstration, and you should summarize that in the report. Yes, Praveen, it's clear? Wait, sorry, you can submit, right? So as much as you can write, but then it should be in your own words. Simply copying from somewhere will not fetch any marks. Yes, Praveen, is it clear? Yeah. Yeah. So you can also add what Mr. Sangan Rangan is saying. So you can add what are the typical applications of that process. Like I talked about the MIAB, isn't it? So MIAB welding, we primarily use to weld tubes, pipes and rods. And some applications you can identify, you can also give where typically the process you have seen is going to be used. Yeah, any other question? Okay. Okay, so if not, we would first start lab visit. Okay, I will show you starting from Glebel. We will walk along the lab and a basic introduction about the lab. Okay, so first we'll see what are the facilities are there in our lab. Yes, shall we do that? Good. Yeah, so we'll move. So I'll introduce our technicians and TAs of the lab. So we have a dad with the GoPro. Okay, so we have a Tausif there, Mr. Rangan, Ms. Niveta and Mr. Prakash. Okay. Yeah, so we have one more technician. Hey, hello. Hi, sir. So we have Rajesh here. So Rajesh is our welding technician, and Mr. Rangan is our technical superintendent. Okay, so we have a big team here to make yourself comfortable in the welding lab. Okay, so once you can have the good. Yeah. Hi guys.
Kind of lab too.
What's that? Okay, so we are now here in Glebel lab. So Glebel lab, we have, this is one of the most used Glebel facilities in the country. Okay, so this lab we set up using our GST funding, and we widely use it for physically simulating various material processing we do to produce, okay, so primary components, primary materials. For example, if you want to simulate a continuous casting facility, okay, or if you want to simulate a hot rolling facility, and if you want to simulate a forging, okay, so we can subject alloy with the thermomechanical cycles. We subject them in a primary production. Okay, so this facility is very unique in the country, right? So we also use this to simulate, okay, thermal mechanical cycles. We subject a composition of alloy. Okay, so we can also carry out a controlled heat treatment. We can also carry out phase transformation studies, high temperature properties evaluation, okay, hot tension, hot compression, okay. So, and we can also construct CCT diagrams, okay. We can simulate, as I said in the earlier the slides. So we can also use this equipment to simulate heat temperature zone of a welding process. Okay, so this equipment comes with a hydraulic loading mechanism. Yes, go ahead. Let me see. And see, not to worry, because we are recording in GoPro, okay? And I will share the GoPro as well. So let me see if it is recording maybe there. So, but anyway, so you can show the GoPro recording. So GoPro recording is there. That is, I'm going to share everything. Okay? Yeah. Good. So Jack, come over here. Okay. So what you see here is the primary console, which is a control console, where we can, we have industrial computer, and this computer, controls the thermomechanical cycle we impose on a sample. Okay, so we have two modules in Dribble. So right now we have installed what is known as a pocket jaw module. Okay, so this pocket jaw module we use to simulate, okay, a controlled thermal cycle with some mechanical loads. Right? Suppose if you want to simulate a phase transformation, we can subject a sample to controlled heating and cooling, and we can attach a dilatometer. Okay, so you know that when the material undergoes allotropic transformation, we expect some volume change. So we can precisely measure the change in volume, and that would indicate at what temperature, when you are heating up, for example, you want to measure the oscillations in temperature at a given rate. Okay, so we can understand precisely for a given heating rate at what temperature this allotropic transformation is initiated, okay, is starting, the onset of transformation. Similarly, as a function of various cooling rates, we can precisely measure the start and end of transformation. Okay, if you want to predict the MS temperature, for example. Okay, so we can impose a typical cooling cycle, and then subsequently we can understand as a function of cooling rates how the phase transformation kinetics evolve, right? And we can also use the same experiment for high temperature testing. So this one sample I showed here, and this is a sample. We use it for high temperature tensile testing. Okay, the important advantage of this is we can attach or we can spot weld thermocouple on top of on a location, and we can precisely control the temperature thermal time cycle using this control thermocouple when we attach a thermocouple. And then we can take it up, we can heat up, and this equipment passes, okay, high frequency alternating current through the sample. So sample is heated by resistance heating, Joule heating, isn't it? So what is Joule heating? I square R T, isn't it? So we pass high frequency alternating current, and the sample gets heated up by resistance heating. Okay, so during this process, okay, sample heats up, and the thermocouple attached to the sample, welded to the sample, would get the feedback from this industrial computer, right? And we can precisely control what heating and the cooling thermal cycles we want to control. Now, if you want to do a tensile testing, okay, what do we do? Suppose if you want to take it up to 12 degrees centigrade, and you want to understand the you want to measure the flow stress at that temperature. So we heat up, okay, we control the temperature, and then we can hold the material at that temperature and then pull it. So this equipment can give 10 ton of loads in tension, 20 ton in compression. Okay, so it's not only a single thermal cycle, so we can also do multiple pass thermal cycles. Okay, for example, so suppose if you want to simulate a forging condition, so this is one sample we use it for compression testing. So this is a 10 by 15 mm cylinder, so 10 mm, okay, it's diameter, 15 mm height. Again, we can attach a thermocouple and we can compress it at various temperatures. Okay, at a given strain and strain rate, we can get a flow behavior. Okay, at an isothermal condition. So you can also change several temperature steps. We can do a 10% deformation, say at 900 degrees centigrade, and cool it to another temperature, okay, at 800 degrees centigrade, and you can give 20% deformation, so on and so forth. And that is typically to simulate, for example, hot rolling. Where if you have a multi-stand rolling mill, and you want to understand how material behave, material deform, okay, as in real life. So that's why this is called physical simulation. Okay, we are simulating the physical condition which is actually generally prevailing in a steel making mill. Okay, good. So various modes of testing we can do. We can also do plane strain compression as well. Okay, so these are unmills. We use it for plane strain. So we start from a sample, so something like a small rectangular sections, and then we use these unmills, which we can use it to apply a plane strain compression loading. Okay, so plane strain loading conditions are prevailing. Okay, so which of the manufacturing processes can anyone tell? Where do you have plane strain conditions? Yeah, exactly. So rolling or forging. Okay, so we have a plane strain condition, isn't it? Loading condition. So we can also get plane strain conditions simulations carried out. Physical simulation. It's not mathematical simulation, isn't it? You are physically simulating. Okay, so some of the samples what we use for hot tension test, and these are the samples we use it for dilatometry. Okay, so we can attach an LVDT, okay, onto the sample, and the sample can be heated up, and then subsequently we can subject varying cooling rates. As a function of cooling rates, we can see how the dimensions are changing. Okay, so if there is no change in dimension when the sample is cooled from elevated temperature, what does it indicate? Yes, guys? Hello? Anyone? Okay, but do you expect change in dimension? Yeah, it's a negative coefficient, negative thermal expansion, right? Of course, sample would shrink, right? But that shrinking would be more or less linear, isn't it? That's why you call linear thermal expansion. So when you're heating up to elevated temperature, when you cool down, you expect the dimensions should vary linearly. If there is an abrupt change in slope, okay, so then what happens? So you can say that, so a material is undergoing some other phenomena other than negative thermal expansion, isn't it, when you're cooling? So that indicates some phase transformations. Okay, so these were these we use for understanding phase transformation kinetics. And so we have two modules, as I said here. So this is a pocket jaw module. There's one more module you see there, you can see, and this is Hydra wedge module. Okay, so what is Hydra wedge module? So Hydra wedge module, we use it for high strain rate deformation, right? So the strain rates more than, okay, so if you want to subject materials more than say a 10 strain rate, it is very difficult with the the setup what we saw in the pocket jaw. Okay, for high strain rate deformation, theoretically we can go up to 80 aluminum at say elevated temperatures. We could even touch about 90, 95, but safe limit would be about 80 strain rate, okay, per second. Okay, we can go using this equipment, and this we use it again to simulate, okay, forging, for example, right, or high strain rate deformation. So we can use this and multi-step, multiple temperatures, okay, with varying heating and cooling rates, we can simulate. And we can also do simple heat treatment. Okay, so that is nothing. Okay, what you see over here is the specimen chamber. Yeah. Right, so the sample goes inside. When we have a demonstration, we'll have much more detail. No? We'll have a closer look of the demonstration. Okay, so when you see in that class, I think 4th or 5th week. And this chamber is, we can also maintain controlled atmosphere. It can be vacuumized, okay, or you can also fill it with inert gas. Our sample can be also cooled with rapidly by water quenching. You can also do air cooling, okay, air quenching or inert gas quenching, so that we can achieve required cooling rates. We can theoretically, this equipment is capable of heating at the rate of 10,000 Kelvin per second. Okay, so, yeah, 10,000 Kelvin per second you can do, right? Yeah, so that is theoretical limit, right? So as fast as if based depending on your sample dimensions, okay, so we can heat up the heating rate we generally encounter in welding. Okay, so that will be typically about 300 to 400 Kelvin per second. Now if you use a thin samples, that should be possible. Okay, so this is Glebel. Then we'll move to next equipment. Yeah. Okay, so we have the next equipment here, so which is resistance spot welding equipment. Okay, so this is the conventional resistance spot welding, right? And we have two equipment, as I said, right? Another one is the delta spot. Okay, so now we'll have some closer look of the equipment. So what is the principle behind resistance spot welding? So we have thin sheets, right, to be welded. So this is a weld made using this equipment. Okay, so we have about 1 mm thick advanced size 10 steel plate. So it must be a dual phase steel of one of our students. So we have two electrodes, copper electrodes, which are water cooled. You see this? It's water cooling. And this is top electrode and bottom electrode. Okay, so we keep the plates to be welded. Between the electrodes, we apply again an high frequency alternating current. Okay, and three important process parameters here. What are they? Yes, Karthikeyan, from welding processes, anyone can say. What are the basic three parameters we vary here? Voltage? Voltage? Do you think voltage can be varied here? Who's answering? No? Come on, guys. What are three basic parameters we vary in resistance part? Welding current, load, and welding time. Exactly. Okay, so we vary welding current, time at which we pass the current, and the load we apply. Okay, so load would indirectly dictate the heating, isn't it? Because the heating is primarily carried out by contact resistance. Okay, contact resistance between the fraying interfaces. More the load, less will be the contact resistance. Load increases, contact resistance decreases. So therefore, higher the load, okay, more current or more time you need to spend to get a required welding diameter. Okay, three parameters we vary: welding current, welding time, welding the load we apply from the electrodes. Okay, so the process is very simple. So we have copper electrodes here, which are water cooled, and these electrodes, they don't melt. Okay, the electrodes do not melt. So we place the plates to be welded, and we pass the current at a given time. We apply a load, we get a nice weld. As I said, so this is by far the largest number of welds, if you look at in the world, number of welds, not the length of the weld, number of welds, resistance spot welding beats all the welding processes hands down. Okay, because as we speak, in Chennai alone, we may be making crores of spot weld just in 30 minutes of this class. Okay. See, the other unique equipment what we have here, this is a variant of spot weld. Okay. So if you look at the other process, there the copper electrodes are solid electrodes, it's fixed. Whereas in here, we have strip electrodes. You see here, the electrodes can be made as a consumable here. So what is the advantage? The biggest problem in using the copper electrodes over here, most of these automotive steels are zinc coated, isn't it? So we have a zinc coating on top. See, if you use a copper electrode for zinc coated steel, the zinc from the surface can diffuse to copper. Okay, copper and zinc. Zinc diffuses copper. What happens? Then copper is no longer copper. Okay, it becomes brass. So locally, the resistivity at the electrode bit on the top surface changes. So if you keep welding, if using the copper electrode, after carrying out a few welds, even after 5 welds sometimes, okay, the prevalent resistivity of the system changes. So therefore the weld properties, weld dimensions would change due to this degradation of the electrode. Okay, so therefore this is a very unique process where every time we can change the position of the electrode, location. So this should rotate. So every time, so now we have one spot, okay, and the next weld if you do, and this can be made to change. So every time we expose to fresh spot. And added to that, we also increase the number of contact resistance locations we have. Okay, in conventional process, top and bottom interface between the electrode and the top surface, bottom surface to the electrode, the heat is generated is actually transferred by the water cooling. Okay, whereas in here, the heat can be generated from the 3 interfaces. So with a low current, we can achieve a similar diameter than what we use in the conventional resistance spot weld. Okay, so these things we'll see in when you have the demonstration of the equipment in live, how they are going to change, what are the influence of welding parameters and the method generation and so on and so forth. So Mr. Rangan will give you the demonstration. Good. So we'll move on to the next equipment. So next equipment we are going to see is MIAB welding. So what is MIAB? Anyone? Come on, what is MIAB? Yes, Zito, you are the only one who answers. No one else is answering. Anyway, no problem. So this is a magnetically impelled arc butt weld, right? So it is a variant of flash butt, right? So what we do now is process. So we use a circular geometry workpieces. Okay, so we have here a pipe welder. You see this, the weld joint made, okay, by using MIAB process. Okay, so we keep over here, right, with the preset gap. Yes, you see here the preset gap, and then you have 2 permanent magnets here. So this is a magnet and this is also a magnet. Okay, so this comes down and clamps the workpiece, and with the preset gap, okay, so with the preset gap, if you pass a current, so what happens in a conventional flash bed, due to the skin effect, the arc is struck only at the selective locations due to the skin effect. So therefore, in a conventional flash bed, when we do, the heating across the cross section is not uniform. Okay, so we need to do something to impel the arc uniformly across the cross section, and by doing so we can enhance the heating efficiency, and the temperature can be homogenized along the cross section much more effectively, isn't it? So therefore we use permanent magnets here. So these are the magnets, you see. Okay, so it's very difficult to pull, right? So these magnets, what do? Again, you can see in the demonstration, they would impel the arc surrounding around the circumference of the weld. Okay, so by doing so, we can increase the efficiency of the heating, and then we can reduce the current required for arcing, and then we can also enhance the welding efficiency. Okay, so we pass again the current using these power sources. These are Lincoln power source, and they can give up to 1800 amperes of current. Okay, each one can give roughly 600 amperes. We can play around these power sources, and we can vary the current during arcing phase, and we can reduce the current during upsetting phase, and then we can carry out welding of circular geometries. And this is very unique equipment. It's made from Petron Welding Institute in Ukraine. Okay, so you know that some of you, those who attend the welding process, the Petron Welding Institute history. It's one of the oldest welding institutes in the world. Okay, continuously in operation from 19th century, right? So some very unique inventions for welding industry is it has come from Petron. Okay, so this is the control console, which you can use it to change the arcing current and current during upsetting distance, upsetting time. So all these things can be. Again, you will see in the demonstration much more neatly. So then we'll go to next. So what you see over here is gas metal arc welding setup. Okay, so gas metal arc welding, we also call that as a MIG welding. Okay, magnet metal inert gas welding, isn't it? So in gas metal arc welding, what we do, we use consumable wire. Okay, so you see here the wire is tipping out here, isn't it? This is a contact tube. This is welding torch, right? So we see consumable wire, and right now we have loaded magnesium. So magnesium wire of 1.2 mm diameter is loaded here, and we strike an arc between this consumable wire and the substrate or plate to be welded. The arc is struck, and during its process, the consumable is molten, and the molten droplets is detached and then deposited onto the molten pool. Okay, substrate is also molten, and more amount of consumable is also molten and deposited. Right? So the entire process is controlled by the power source. So this is a typical welding power source. So this is a Fronius made power source, and this power source is also capable of creating various types of metal transfer, droplet transfer. What is droplet transfer? How the molten droplet is detached and deposited, isn't it? So we can do it free flight transfer. We can also do it in a dip transfer, where the consumable with the molten droplet at the tip can also be dipped onto the molten pool, and then we can detach the droplet. Okay, so all these things are nowadays synergically controlled. Okay, in old days, when I started my PhD, the synergy control was not there. We have to manually develop the waveform. We can we'll have to give it to the power source, and then for a given waveform, we can see what is happening. Nowadays, energy control made life easy, but it also made welding engineers less knowledgeable than in my generation, engineers. So here you can set up only by 3 volts. You can mean current. Okay. So wire feed rate and mean current you can set it up, and rest the power source, the microprocessor inside the power source would calculate and then control the process. Again, we will have a demonstration of this process, both in conventional gas metal arc weld, also with varying process parameters and metal transfer characteristics, both in free flight, in dip transfer. Okay, so next process we are going to look at is plasma. Okay, so plasma, this is a power source for a plasma, and also you can also use this for a gas tungsten arc weld, TIG gas weld. And this is the high power plasma torch. Okay, what is over here? And this torch is also water cooled. So why do you have to water cool? Because you see here, so this is water cooled copper nozzle which constricts the arc. Okay, some of you must be aware. So we have a tungsten electrode here, an arc is struck between the electrode and the base material, then it's called transferred arc, isn't it? Right? The transferred arc is struck between this, the tungsten electrode and the base material. Sometimes we can also strike an arc between the tungsten electrode and this nozzle. Okay, you can make the tungsten electrode is negative and this is positive, then it becomes non-transferred arc or pilot arc. You see here the hole, and this is where we constrict the arc. Okay, if arc is constricted, okay, we promote more collision, okay, between the ions and electrons. Okay, so then arc can be converted into plasma, isn't it? What is a plasma? What is the difference between arc and plasma? Anyone? Yeah, plasma is neutral state, isn't it? Whereas the electric arc is negative. So there are more electrons in a conventional welding arc than ions. So ideally, welding arc is negative, whereas plasma is neutral. So we enhance the coalition so that the arc can be converted into plasma, isn't it? And here, this collision is enhanced by the constriction of the arc. Arc is constricted, it's made to go through this nozzle, water cooled copper nozzle. Okay, so that creates a near plasma. So technically, if you measure, no, this is also negative, but still we can call this a plasma because almost towards equilibrium we can achieve. And this is an high power plasma. We can get energy of. Okay, so we'll continue quickly. Right, so this is the plasma setup, what you have seen. So this is plasma power source, and this is high power plasma torch, isn't it? And we also have another setup, which is a microplasma. So this is a microplasma torch, what you see over here. Okay, so you can see the orifice is much smaller diameter, isn't it? So this is now 0.6 mm, Prakash? 0.8. 0.8 mm opening. So arc is struck, the tungsten electrode is inside, okay? And the arc is struck between the electrode and this torch, then becomes non-transferred arc or pilot arc. Or we can also keep a base material here. We strike an arc, because of this constriction, it becomes plasma, right? And then subsequently, we can reduce the current in such a way that we create a very small, tiny beam of plasma. So if you use 0.8 mm orifice, the plasma that comes out will be roughly, at the tip will be 0.8 mm, isn't it? So it gets diverged. So roughly about 1 mm diameter of plasma with extremely high energy we can generate, right? So this plasma power, if you use say 30 amperes of current with the working voltage of 15 or 20, 600 watts of power we can generate. And 600 watts of laser would be much more expensive. And here the energy absorption efficiency for plasma is much higher. 600 watts if you send, almost with the efficiency of 90%, this goes into the material to melt to the work. Okay, so therefore this is much more energy efficient than laser. And we can feed the wire. Okay, so we can also use this as a consumable process, right? So we can feed the wire, and then this wire melts, the molten wire is deposited onto the base material, right? So this process nowadays we are actually exploring for additive manufacturing. Okay, so we can use a feedstock, and feedstock can be molten and deposited based on the region we were going to create the layers. Okay, so we'll see the demonstration when we go there. Okay, when we start. So the next process we are going to see is the gas tungsten arc weld, okay, or TIG weld, right? So TIG weld, what do we use? This is a non-consumable welding process because the electrode doesn't melt. In a gas metal arc weld, the electrode melts, isn't it? Here, okay, so we use a tungsten electrode. See over here, and this tungsten electrode is used to strike an arc between this electrode and the base material, right? So this is a contact tip, the electrode, and we pass the shielding gas, primarily argon, through the starch. Okay, and then the moment you strike an arc, break it down. Okay, and we can do welding manually in autogenous mode. What is autogenous? Autogenous mode means without any external filler. Okay, or you can also add filler by mechanized setup, or by using hand you can add the filler. Right, so we'll have a demonstration when we do this weld, and during this process we'll also attach thermocouples to measure, okay, the temperature cycle that is prevailing. Suppose if you pass the torch and we weld, and you can attach the thermocouples adjacent to the weld zone to measure how the thermal profile evolves. Okay, good. So then we have frictions welding. Okay, so this is a solid state welding process, right? So in this process, so we use a tool which made to rotate across the faying interface. Okay, so what does it do then? Suppose if a material to be welded or to be joined, okay, by solid state process in the friction stir welding, the tool plunges onto the material to be welded, and then we make rotate with an axial roll. So the material flows, the coalescence created from one interface to other interface by the mechanical deformation in solid state. Okay, so this is a process nowadays widely used for welding of aluminium. Okay, primarily. For other materials it's still not established. For aluminium it is almost most commonly used process. Okay, so with this we will wind up, and we'll move on to the first demonstration, which is manual metal arc welding. Okay, yeah, Prakash, you want to start? Rajesh, what do you do?
Yeah, we'll start this.
We'll start, right? Okay. No.
Whether today is demonstration or we have to...
You can show, you can show. Okay. So what you see over here is again the welding power source we use. Okay. So this is the power source in general for TIG, MIG, conventional MIG. We can use similar power source. Okay, because we want to draw current at a low voltage, right? So these power sources can give us, for example, can give up to even 3000 amps, both in alternating current and direct current, with the operating voltage of about, okay, so 20 to 30 volt. That's what we have. And in this process, in a manual metal arc welding process, we use thick electrodes. Okay. So this is a stick electrode, right? So the electrode number is given here, E7018.
Low hydrogen.
Yeah, so E means, so that is the electrode, the MMAW electrode. Okay, 70 denotes the ultimate tensile strength you may get when you use this electrode on the weld. Okay, so you'll get 700 megapascal strength. Okay, so next numbers indicate its percentage elongation. Okay, and so on and so forth. Right. So what is so special about this electrode? Right. So we have the flux deposited onto the electrode, and we have a metal core. So because of the shape, like a stick, so this process is also known as stick welding. Okay, so stick welding is a common term used in US. So US, and if you go and tell manual metal arc welding or sheet metal arc welding, they don't understand. Okay, so like they don't understand mm or a kilometer. Okay, so they always call it stick welding. Okay, so these fluxes used on top of these wires, they are also used to generate shielding gases. Okay, so we don't use any external shielding in most of the cases. Right, so the fluxes used can be many types. Common types are, okay, basic electrode, rutile electrode, cellulosic electrodes. Okay, so this looks like, for me, it's a basic electrode, right? And basic electrode typically use fluxes made using calcium oxide, calcium carbonate, okay, or calcium fluoride based fluxes. Calcium carbonate, when you heat up, is disintegrated into carbon dioxide and calcium oxide. Calcium oxide is the slag which forms on top of the molten coal, right? And this slag can protect molten coal from oxidation. So slag metal reactions which can control the oxidation, right? The carbon dioxide is generated from the decomposition can be used for the shielding purposes. You can strike an arc. But for strike an arc, you need a gas. And the rutile based electrodes, okay, so we can also use them for non-carbon steels. Okay, because rutile based electrodes generate hydrogen. Hydrogen plus carbon dioxide can be used for shielding, okay, for arcing. And cellulosic electrodes are also cheaper. They use hydrocarbons, natural hydrocarbons. Again, we generate hydrogen and the carbon dioxide with cellulosic electrodes. Okay, so we attach. Okay, so the electrode. Okay, so now Rajesh is going to take over for the demonstration.
Yeah, good afternoon everyone. So here we have the motor generator set. This is also called a arc welding machine. I'll show the construction of this welding machine here. So we have various kind of arc welding machine here. One is rectifier and one is this is a generator set. Okay, I'll show the construction of this welding machine. This is the motor generator set. This is not a regular rectifier or the normal arc welding machine. Okay, here the motor will rotate and it will give the output as the DC current here. So this is what called the motor generator set. This is very old machine, nearly 50 years old. This machine. Okay. So here we have two terminals. One is positive and one is negative. So generally for welding of the stick electrode, we need two terminals. One is positive and negative. The positive will goes to the electrode holder. So this is the electrode holder what we have here. Here we will fix this electrode. And then the negative terminal is connected on the work table. Okay, this is the work table, what we have here. Okay, so I'm going to use a rutile coated electrode. So each and every electrode we have a specification. So before proceeding welding, we have to see the specification of this electrode box. See, it is mentioned E6013 is here. Okay, so E stands for electrode. The first two digits stands for the tensile strength of the weld material, and the third digit stands for what are the types of position we have to use it. Okay, and the final digit it says the flux covered.
Yeah, so the digits over here based on the classification. Okay, so what you see here E6013. And this is an American standard because these electrodes are actually from AWS standard, right? 60, the ultimate tensile strength, okay? And the first digit indicates its uniform elongation, okay? The weld properties. You can, okay, so I will share the designation, right? Or if you have attended my welding processes, no, the slides must have this information, okay? Let me share the specification in the Google Classroom, okay? Yeah. Because these numbers can be, changed based on which standard we use. These ESAB, they use AWS standard, but there are some electrodes, if you buy from, for example, a Voestalpine Buller, they use European standard, more of a British standard, okay? It can be changed. Okay? The first two digits are important. First two digits indicate the tensile strength, weld strength. And the third and fourth digit, based on the manufacturer, it can change based on the standard. Okay, go ahead.
Yeah. Now I'm going to weld these two mild steel plates. This is 6 mm thick plate. The plates are beveled. Okay, why we are going for beveling these plates? If you are crossing more than 3 mm thickness, then we have to do a beveling. Otherwise, we will not achieve good penetration. For achieving a good penetration, we need to do a edge preparation or beveling. Okay, so this beveling is also, we have certain standards are there. We have the AWS standards. So as per the standard, we have to do this edge preparation. Okay, right now the plates are edge prepared already. What I'm going to do, I'm going to join these two plates. This is called a butt joint. Butt joint, and what position is, this is a down hand position I'm going to do a welding. Okay, if the plates are fixed in a vertical, this is a vertical position. There are 4 types of positions are there. So now we are going to do a down hand position welding. Okay, I have chosen this mild steel electrode, mild steel base plate. So we have to choose the mild steel electrode for this welding. So what we have to do is, we have to take the electrode holder and we are going to fix the electrode in this position. The electrode should be in perpendicular. Why? Because we are going to do a down hand position welding. Okay, already the earth cable is connected, the ground is connected on the work table. Okay. Before start welding, we have to follow some safety precautions. We have to use proper shield, hand gloves, and then goggles, everything. Why? Because the arc will produce the UV rays. Those UV rays will affect your eyes. Okay, to protect your eyes, you have to use the 11 bisque dark glasses for welding for arc welding. So I'll get ready.
Yes, go ahead. Yeah, when you use the square bit for smaller thicknesses, you can technically use. But the demonstration purposes, this is only common. Okay? Yeah, you can do square bit as well, but the square bit only the root penetration is difficult. But 3 mm is tricky, you can still make it. But 2 mm square bit is tricky. More than 2 mm better. Otherwise, you have to root pass by feet and then do less by the root.
So we need to wear the hand gloves and then apron. These are the main important thing. Otherwise, this UV ray will affect your skin. It will burn your skin. So I'm ready with my safety things. So now I'm going to start the welding machine. Before that, based on the thickness of the electrode, we have to set the current. So here setting the parameter is very important. The wire electrode, the wire diameter is 3.15. So based on the thickness of the wire, we have to set the current. Why? Because if the wire diameter is too much thicker, if we set the minimum current, the wire will not get fused. For that, we have to set a recommended. So for this 3.15, I'm setting the recommended current is 100 to 120 amps. So I'm setting 120 amps current. Now the machine is turned on.
What the type of
And then here we are using the reverse polarity. There are two polarities are there. One is straight and one is reverse polarity.
Hold on. Yeah, go ahead. His voice probably better. Okay, so. No, I'm also near the camera only. Okay, so you can also.
Sir, any questions?
You are lighting it. Switch off. You can put in your.
So Mr. Rangan is giving this headphone. So Rangan will speak after.
Don't worry. So questions they will not ask.
So I will
just to answer.
Is it better now?
Just audible
Yeah,
please.
it's okay.
Okay, I'll just go back.
So we have two polarities. One is straight and one is reverse polarity. Why polarity is important here? Do you know what is polarity? Okay, I'll tell you that. In reverse polarity, the electrode. Sorry? Yeah, here, why we are using reverse polarity here, I'll tell you that. See, here we are going to fuse the electrode. We are not going to, we are going to fuse the electrode and we are going to deposit on the base material. Okay, for that, we are going to use a reverse polarity here. Reverse polarity in the sense of the positive terminal is connected to the electrode. Okay, the negative will be on the work table. Where positive is connected, more current will flow on the electrode side. Okay, so that the electrode will fuse more than the base material. We need not to spoil the base material much. We are going to fuse the electrode and we are going to produce the weld on the base material. For that, we are using a reverse polarity. In straight polarity, the electrode will be negative and the base will be a positive one. Or some other process. This is a completely permanent joint. Okay. For that, what I'm going to do here, I'm going to make 2 tacks. Why tack is required? If I start weld like this plate will start to expand in the opposite side. For avoiding that, I'm going to make a tack on both the ends. So tack is a temporary joint only. Okay. So there are 2 methods of initiating the arc. How to initiate the arc? There is one is tapping method, the another one is scratching method. Okay. So before bringing the electrode to the base metal, which means on the negative terminal, bring the electrode closer to the negative terminal and look at a shield. You guys, you do not have the shield, so the arc will not clear to you. If you come to the lab during that time, you will be seeing this. Inside the shield, this is visible. Can you keep the shield here?
I don't think it's possible.
It will not work.
You can pull it out. So you see the
Yeah.
tag is done now. So these are tags. We have done the tag welds. The tag weld is nothing but we actually do it to just to create a clamping condition. Otherwise, what you do when you do start welding, because of the residual stress and distortion that is developing during welding, you will have two plates would be splitting or separating when the welding is actually done. Go ahead.
Now the weld is completed. You see the electrode is completely, it's melted. It's 350 mm length. The complete electrode is melted for this much length of the weld plate. So this is, we call these chop-in.
What is our given top? These are slag. This slag is a self-lifting slag. Okay? Rutile electrode. That is rutile.
Yeah, this is a rutile electrode, yes.
So you see over here, it's a self-lifting slag. Then the basic electrode, slag is sticky and slimy. So for basic electrode, slag removal can be a bit tricky. You need to do a grinding. Whereas rutile, the electrode is generating the self-lifting slag. So rutile is titanium oxide, isn't it? So it becomes very easy to remove slag. So the occurrence of slag inclusions would be minimal in rutile-based electrodes.
Okay, why flux is required is here? To protect the molten material from the atmospheric air. Generally what will happen, without flux, if you try to weld it, it will create a failure joint. Generally what are the failures will occur in the weld joint? Yeah, blowholes, cracks. Very good. Yes, not lack of porosity. Pores will occur in the weld joint without flux. For that purpose, flux is introduced here in arc welding. Okay, generally in in TIG welding or MIG welding, we use the external gases, that is inert gases, argon and helium. So here we are using the flux as the to protect the molten metal from the atmospheric air. We are using a flux to cover the weld material. Okay, and then how to maintain this distance between the plate and the electrode. This is a consumable metal wire. You see, initially the length of the electrode is 300 mm. Okay. If you start the arc here, the electrode keeps on melting, which means keeps on reducing. So you also, what you have to do, that gradually you have to bring your hand towards the base metal, like this. Okay. Otherwise, if you are maintaining too much height between the base metal and the electrode, you will not get a good arc, or otherwise the arc will not occur during welding. I'll show you that also, what it is happening. Goes out. So how will you identify that? What is the distance between the base metal and the electrode? Arc gap, that is called the arc gap. What is the diameter of the filler wire? What is the diameter of the filler wire, or what is the thickness of the filler wire? Based on that, you have to choose the distance. My filler wire diameter is 3.15, so you have to maintain with that gap only. Then only the arc will generate. If you raise the electrode too much higher, you will not achieve the arc. So for that, you have to maintain the arc length should be very minimum, the arc gap. R gap is nothing but the distance between the base plate and the electrode. Sir,
Done?
yeah. Anything else?
Yeah, so guys, any questions so far?
Cool the plate and connect.
Yeah, so we have made the first demonstration. I think this is the process. Now you must have also trained in your bachelor's, or no, you must have seen anywhere. If you go for a fabrication facility, for example, if you want to make a gate, a grill or window for a house. I will make you that the fabrication technique. As well as most effective, most used process fabrication. So Rajesh is a very skilled welder. So see the quality of the weld. Okay, excellent.
Now these two plates you can't able to segregate now. That's why this is called the permanent joint. Okay. Could you able to segregate now? Both the edges are fused and then it is jointed properly. So generally we will call this is a weld zone, this is a heat affected zone, and this is a base material. So what we call the backside, this is called the penetration area. We have to maintain a uniform gap, then you will achieve the complete penetration at the backside. For that we have to use the jigs and fixtures. So roughly we welded here, that's why we are not achieving complete penetration at the backside. You see the weld height, and then what is the width of the weld bead, everything is uniform from the starting to the end. So do you have any doubts so far?
If not, yeah, go ahead. Go ahead. That is R gap, right? R length. That is the characteristic of control waveform, of very large circuit. So that is like, if you look at the current voltage characteristic in discharge, right, we have a typical characteristic curve repeated, right? Continuous. So for a given arc length, we get a defined voltage. The current what is set, it should intercept with the voltage line. That's what we call grouping characteristic of a power source. Okay, a power source and the gas, shielding gas, they define how the current and voltage vary. You have paper and pen. Maybe I can use the iPad. Okay, so share my screen. Okay, you can full screen. Okay, so the recording is going on. You can give the pen is there. Okay. So hold on. I'm going to get the pen. You have a typical characteristics, right? So we have here voltage and current. For a given, hello, who's that? Okay, so for a given shielding gas,
we develop a typical current voltage characteristic, isn't it? Right? So the arc length, the gap between the tip of the electrode and the base material, that defines the arc length. If you change the distance, voltage is changed. But Rajesh, from the power source, he set the current. So imagine, so he's setting, Rajesh, what the current you said?
120 amps.
120 amps. Right. So for 120 amps, the voltage which is generated from the system means the welding circuit, that is determined by the arc length and the shielding gas. Okay, so what gas is prevailing between the arc gap. So this is a typical discharge characteristics we generate. So he already set current to 120 amperes. So for this 120 amperes, so we have the intersection somewhere here, isn't it? So what happens, suppose if you move the length or the gap between the tip and the base material, so the voltage would change, isn't it? So when the voltage changes, what happens? You would be increasing the voltage. For this set current, then the discharge will not happen, isn't it? So this is a typical discharge characteristics. If discharge doesn't happen, that means that arc would extinguish. So there will be a range of voltage in which you can operate for a given current. So the arc length would dictate, okay, so the voltage what we are going to develop in the welding circuit, because voltage is a derived parameter, mind. We always set current. Voltage is generated by the shielding gas and the arc gap. If you change the arc gap, voltage is changed. When the voltage is changed, current has to be changed to different ranges. If you set 120 amperes, you can only strike an arc in this region. Otherwise, arc will extinguish. Okay? Is it clear? Praveen? Yeah. That is what training is, right? Skill. Okay, so that's how welding is skilled job. That's why you need a certification for doing welding. Okay, without certification, you are not allowed to touch the torch. Right? Yeah. It comes with a... Yeah, so that comes with experience. So that is again characteristic of the power source also. Okay? The power source will also maintain the voltage. Right? Right, nowadays the rectifier based, inverter based power sources, so they have a broad range. I mean, you will not see so typical voltage characteristics of this power source. Okay, so as a function of time, okay, so you may see something like this. Right? So whereas in the rectifier inverter power sources, you have a constant voltage generator. Whereas in here, if you have a time or even current, it can change. So that means that you have a drooping characteristics current develop. So you will have a broad range of voltage you can operate in this case. Whereas so therefore here the maintaining the gap is very tricky. In inverter based systems, it gives much more stability in terms of voltage. Okay, so then you can also slightly vary. Automatically, the current can be adjusted. It may not be 120 amperes. It can be changed so that arc is always on in the modern power sources. Yes, Praveen? It comes with experience, Praveen. So you need to really train to get that excellent weld what Rajesh is saying. Okay, yeah, good. Any other questions, guys? Okay, so if not, we'll wind up, right? We'll see you next week. I will upload the videos. Okay, I'm not sure whether Google Meet video is available, but we have the other better camera, which we have made recordings. That will also be uploaded, and the slides. And someone asked about the electrode classification. I will also upload those. Okay, good. Good, guys. Any other questions? If not, we will thank the technicians, Rajesh, Rangan,
Okay, our TAs, Jag, Mitra, okay, sorry, Niveta, sorry, Niveta, and then Prakash. Yeah. Okay, good guys. See you next week. See you next week.